Only 140 slides, so. So the more you guys know about the spec books, the less time I have to spend on them. So does everybody know the spec book inside and out? Well, if you can read every other section, you can read the project. Yep, that's all I ask, as long as you know where to go to look. So right here, this is from Greg Bach. This is one of the projects I was on. In foundations, I was in charge of the foundations of the substructure up to the superstructure. So you can see, this is our coffer dam. We have 6 of these on our project. And I was telling you yesterday, river levels here, the bottom of the river is 20, 25 feet down, and we were another 20, 25 feet below the bottom of the river. You can see the rings we have in here. This is all engineered, you know, for the pressures. In here, these sheeting were about 80 or 92 feet. These sheet pilings were. Get that in there. When you're standing down in there, it's a long ways up. And you can see we had our egress. We have 2 egresses in here. You can see the ladder over here, getting up, and then there's another one on this corner. And the nice thing about using these big wide beams, you know, these were 3-foot beams right here. You could walk this perimeter. They put a cable safety guardrail on there. You can, if you're scared, some people can't go down there. I was surprised. There's some people on our project want to do business down in that hole. So you can stand up here and you can observe stuff that's going on down there. We had 42-inch pile, 3/4 and 1-inch thick wall. They're driven open-ended. So from standing right here, the piling, we're about 160 feet down from here. So we had 90 feet below cutoff, roughly, standing in the bottom. Our seals, when I talked about the buoyancy, the bobber, the forces of the pressure coming up inside of there, our seal was 14 feet thick on this project. So we excavated down to the bottom of our footing elevation, right? Well, now we gotta go another 14 feet to get to the bottom of our seal elevation. And then you can see this is the twin walls. This was a balanced cantilever cast in place segmental bridge. What do you suppose happened here?
Vibrated?
Didn't vibrate it? Didn't get the vibrator down there? They didn't have to redo it, they could patch it. There's so substantial amount of rebar in here. I think we have 3 or maybe 4, you know, because this is 1 pour from this joint to here is 1 pour. From this joint down is 1 pour. This plinth right here, this was 46 or 48 feet tall down into that hole, sticking out. And that was 1 pour right there. I think we have massive pours. We had 18, 20-hour pours to do this. Because it's mass concrete, you know, so you got concrete strengths we have to worry about when we're pouring this. Nope, so this is on the edge on land side. There's another pier right over here. You'll see it, it'll come up again with other pictures. We have 3, if not 4 vibrators still in place on these projects because they get them down in there and they get intermixed into the rebar. You can't get them out. They were using man lifts to try to pull these vibrators out and they just break them right off. So there's some of these twin walls that have some vibrators stuck in them yet. So yeah, just some overview there. I'll have more project pictures. And again, like he said, he was talking. If you got experiences about your projects that you've seen or you had, let us know. Let's talk about it. So your piling, when it shows up on your project, usually at the pre-con, your contractor is going to give you a mill cert. This is where we have to validate the material that he's bringing to your project. We want to make sure it's melted and manufactured in the USA. You got the BABA Act, Made in America, Buy America, I should say, Buy America, Build Better Act. What's that?
Buy America, Build America.
Yep. It gives you your dimensions of your piling. Pipe, 12-inch, quarter-inch wall pipe. Certified, QA at the plant. So when we're talking about heat numbers, we have to trace, if you look on a pile report, there's a column that says heat numbers. We want to track the heat numbers that you put in whatever location are going in. So it's your...
Those are usually stamped on the pile, aren't they?
Yep, we'll get to that, where you'll find them. But when we look at our piling, there's going to be a number stamped, stenciled, a label, and you want to match that up to make sure you've got the piling on site matches your paperwork. If it do not match, they have to get you matching documentation. You can't use it otherwise. So here's an example. HT C18632. That's your heat number. That's one way they do it. It's a stencil on there. This is your PO number, project number. Sometimes you can use these numbers to correlate to a heat number of your documentation. You'll see labels on the plates, on the ends of the piles. You think this is a heat number? What do you think the heat number is now? Look at there, heat number. So just be careful when you're looking at these documentations. Sometimes you're going to reference different numbers they're going to have there. Just one. That could be a batch number, that could be a number that they're using at the plant, how they correlate piling for batches or whatever. But that's the number, that's the only number we care about. Sometimes you have to work through this number to get to this number. But that's the number we're looking for, is the one that says heat number. It tells us grade 252, grade 3, and the size, dimension, quarter-inch wall, 12-inch, 60-foot long. H-pile, same thing. Tells us the size, the length, the grade, and the heat number. Sometimes they'll be stuck on there, sometimes they're riveted on there, sometimes they're wire tied on there, metal plates you'll have on there. So you want to validate and make sure when these show up, when you start laying out for test piles, that there's, like for example here, that you want to make sure those are 60 footers and not 50 footers, 55 footers. You want to make sure you know what you're paying for that's going in the ground. We don't care if this says 60 and this is 55 foot. We just want to annotate that this is 55 feet put in the ground. The engineer will visually inspect. When they show up on site, they will look at the mill certificate to make sure everything matches, and they want to handle and store these pilings so they don't damage them. There was a project this summer, mishandling them. They were denting the piles. It was 12-inch, quarter-inch wall, and they were literally denting the piling. So it's not that you have to reject the whole pile. They need to cut that section out. They can't use it with a damaged piece of pile. The big thing too is galvanized pile. Not too often, once in a while we'll see painted piles show up. Some shops like to paint them over the winter time for summer work. But you want to make sure you inspect the galvanizing and the painting when they show up to make sure they're not damaged. And use proper rigging, moving these painted or galvanized pilings so we're not wrecking. So early on, you have your pre-con meeting. One of the items that the contractor should bring with him is our weep analysis. It's how we qualify the hammers for your specific job, your specific foundation, whether it's an abutment or a pier. This is your first C of what a typical weep analysis is. It's just telling us the assumption, this is all computer generated. It's measured with kips. And their assumption is it's going to take this many blows, with this much stroke to meet your bearing requirement. And if you look at the top, it's gonna tell us our bridge number, location, and which abutment or pier. It's gonna tell us the location. This is done for every location, and it's project specific. So if I have one hammer, I can't use that same weep analysis on 10 different projects. It's project specific. It takes into account your soil boring results, the size of the pile, the size of the hammer the contractor is gonna use, things like that.
You have to have a separate weep analysis for each abutment and pier?
Yes, well, it'll be one weep analysis, but it identifies each pier abutment within the one weep analysis. But they have to identify each element or each substructure per bridge. And again, that's the big thing, this is computer generated. That's why we do a test pile. What's our test pile? Field pile. So if we look on sheet 60, 62, why did she disappear? What type of soils and STP bowl counts are expected at the bottom of the test pile near boring ST81? Okay, next. So if we at the bottom of the test pile do ST81. So we look for a label on the top. On all them borings, we're looking for the ST81 bore log. Okay? There's our piles. If you look, there's a little outline there. That's our assumed pile length. Okay? So now at the bottom of this pile, right here, what's our soil type? Here's different answers.
Poorly graded sand.
Poorly graded sand. Okay, what else? we got?
So,
One clay and one poorly graded sand. Okay, the way we read this, I just moved the pile over. It's the same pile, I just moved it over. So now, we go to the base of our pile, we gotta go over here to our boring. We wanna look at our bore log. So the end of our pile is in this increment, right? Where does our line go for this increment? What's that tell us? Need clay. See why I moved it? So you want to come to the base of your pile, I moved it into our board. It's in this region. But look at how our lines go for this region. See that? Let's pick up here. See that? If our pile ended right here, look at our region, look where our lines go. It's poorly graded there. So you gotta make sure you look, you can't read it where the end of your pile is, you gotta come over to the boring log and see what layer you're in and follow the lines above and below where you're at. So it's clean clay with layers of silty sand, silt, very stiff, wet, muck, loon poop.
No, loon poop, the pile just sinks in that loon poop.
Yeah, that too. So that's the assumption. When we do faders or foundation recs in the bridge office, this is what we're assuming, we're guessing, we're hoping the pile is gonna end up. There's no engineer mathematical equation that tells us this is gonna stop right here. There's nothing in the world that will tell us this is gonna stop right here. or that you're gonna even go that far. Stop here, stop here. The engineers take an engineered guesstimate. This is where assuming where it's gonna end up. So that's why we do our test piles, our feeler piles, to validate and verify how long our pilings are gonna be. So everybody understand how to read that? You wanna get to the bore that's closest to your substructure that you're working, it'll be labeled accordingly, and you wanna find the one that's closest to your substructure. Everybody remember doing that in your prerequisite class, looking at this report? So it's lean clay with layers of silty sand. So we looked at that. So when we do our weep analysis, the engineer doing the weep analysis takes that into account, inputs the parameters of the soils going down. So when we submit this driving system submittal to the owner, there's 3 major things we look at on the submittal. It's got to be submitted 10 days prior to driving. Look at number 2. Not more than 90% of the yield strength of a steel pile as driven, right? What did we say shell pile yield strength was? What did we say H pile was? 50, right? So when we're driving, when this weep analysis was built or made, we're driving this pile not exceeding 90% of that yield strength. Piling has to be driven between 30 and 180 blows per foot. Let me rephrase that. Piling has to be accepted between 30 and 180 blows per foot. We can drive it with less blows per foot, more blows per foot, but we have to accept the end bearing between the 30 and 180 blows per foot. Contractor's gonna give the weep analysis engineer the hammer that he intends to use for the project. He'll list the parameters on the weep analysis. There'll be ranges, graphs, all kinds of funky stuff on there. And then we got a pile hammer. Max rated energy of a pile hammer. We can only use 85% of the max rated energy of that hammer to drive a pile. So 90% of yield strength during driving. It's got to be done between 30 and 180 blows per foot. And we can only use 85% of the manufacturer's maximum rated energy. Don't get hung up on that too much. I'll explain more of that, how that works. Again, operating at 180 blows per foot or less at the above conditions. It's right in your spec book. It's outlined as part of the weep analysis. So when you get this weep analysis, this is one of the pages it's going to look like. We have a south abutment, we have a north abutment, and we have a pier. Our hammer efficiency, again, computer generated. This is what they're expecting the hammer to run at. 76 to 80% efficiency from the hammer. Field setting 4. Here's our assumed bottom of our pile tip elevation. Here's our driving stresses that we're putting on the pile during driving at fuel setting 4. This is their assumption of blows per foot, and they're guessing that it's going to be about a 9.4 hammer stroke of that hammer. So, what did we say that hammer efficiency couldn't exceed? 80 what? 85. Yep. 85%. So when we look at this, we want to make sure we're not exceeding 85. What we say, the CIP, say it's CIP, we said what was the PSI for CIP?
40.4.
So we want to make sure we don't exceed 90% of that, right? In that column. And what would we say our blows per foot range was? 30 to 180. We're within the parameters. We don't care about stroke height. That's not a measured factor or governing factor for the weep analysis. So let's go down to our pier. 60 to 80. So they're saying fuel setting 2, the hammer's gonna be running at 60% efficiency. At fuel setting 1, it's gonna be at 80%. Okay? Look what happened here. By reducing our fuel setting, why do you suppose our driving stresses are going up? Why we had to reduce our fuel settings?
Type of material on it.
Agreed. That's all based on the type of material. It could be more resistant, it could be more stiffer. So then your stresses are gonna go up on your piling during driving. So in turn, we're gonna reduce the fuel setting to be below what percentage in this column? 90% of our pile, yield stress, right? Blows per foot. What happens when we get into denser soil? Look what happens. We had to reduce fuel setting because this probably exceeded 180 blows per foot, right? So we reduce our fuel setting, gives us less stress on our pile during driving, and it lowers our blows per foot, right? Look at what it did to our hammer stroke by doing that. It reduces our hammer stroke. So does anybody know what our energy, how we figure out energy on a pile hammer? What is it?
It's your height of your stroke, with the weight of the cap and the weight of the pile. and-
Nope, too far.
Okay.
Too far. Close, you got the first part
Yeah, the
right.
height of stroke.
So the height of the fall of your ram times the weight of that ram,
Oh,
right? The weight times height, W times H, weight of the ram, how high it goes, how far it falls, gives us our energy. So, if we have reduced fuel setting, we're reducing our hammer stroke, which in turn does what? No,
reduces your energy.
energy, reduces our energy, because now, what do we say? Weight times height of fall, right? That's our energy. What's that? So if our height is reduced, what happens to our energy? It goes down, right? If our stroke goes higher, it goes up, right? So that's what a typical weep analysis, when you as the inspector, when you're reviewing this is what we look for. This is what we're looking at to make sure everything's within the parameters. Very rarely will you ever get one that's outside the parameters, but it does happen occasionally, where they just missed it. And then on the bottom, gives you the details, just a little synopsis on it. So, our pile driver leads. Capable of holding the pile and the pile hammer in alignment during driving operations, right? We said that. So the engineer will establish the working points for each substructure after the contractor completes the excavation of the unit. The contractor will stake the pile locations. Say that.
Contractor will state the pile location.
Who verifies them?
Inspector.
Inspector verifies locations. It behoove you to go out there when the surveyor's out there and walk through with him to understand what he's staking, his offsets, working points, things like that. And to walk with the contractor at the same time he's laying out piling locations. So then you understand how he's doing his math and know what he did. Instead of you just letting surveyors stake it, contractor stake it, contractor calls you, okay, my piling's laid out, you wanna come and check it. Now you gotta start all over from scratch, figure out the working points, set string lines, and figure out the layouts. So it's behoove you to walk along with your surveyor and your contractor doing layout. And for me, anytime a surveyor's on site, I like to go with them. So I know and understand what they're laying out and staking on projects. Because when the contractor comes to me, says, hey, what's this stake mean? I know what that stake means and I can tell him. It saves me a phone call to the surveyors, or the surveyor's making another trip to explain a stake. Oh, I guess we're done.
Please, can we go back on the driving stress?
Driving stress.
Yes, please,
I'd love to. No, controller dead.
Or is it battery or
Wreck something.
pressure and killing?
Oh, batteries. Oh,
Plug that laptop.
battery on the computer.
Sometimes, maybe because you could get the same
We're rolling here. There we go. So you had a question on this,
Yeah.
stresses, okay?
I wanted, because, for the string, we did lay that up, we can actually see, for like 80% of the,
So we use 85% of the max rated energy of the hammer, and we can't exceed 90% of the yield strength of our tile.
But, here we have a trade two, some two and three, one. What is one?
Yep, so that's the stresses they're assuming that's gonna be put on the piling during dries. That's their assumption. So if this number is be above our, what did we say, 41.5? If that number is above that, that's not acceptable. We need to be, it could be any number below the 90%. We cannot exceed 90% in that count.
40.5.
40.5. So that number for shell pile has to be below 40.5 KSI. So it doesn't exceed 90%.
Those two.
Okay, any other questions? This is just going right through the spec book. That's all we're doing right now. I'm just explaining the highlights of the spec book.
Yep, I'll get picked up.
Provide foundations to the elevations grade shown in the plan. Use temporary construction. In what kind of condition? Who has the authority to change the elevation of a grade? Engineer. Part of your spec, all the temporary work is at no additional cost to the department. That's all bid in when they're bidding on the project. They take into account what they have to do for temporary works, pumping, heating, everything like that. So this is why I said it's behoove you to go with your surveyor and your contractor to understand staking. See on the left, good old fashioned batter boards and string lines, right? Well, hopefully the contractor would leave that string line up there for you to verify the piling. Otherwise, you're gonna rebuild this whole apparatus on your own to figure it out. Example here, got Interstate 90 right here. Oh, look, we got sheet piling, temporary use. Hold up the roadway so it doesn't fall. See the guy back here? He's on the working point, offset, right? Got a tape measure, good old fashioned string line to the plumb box for his offset. He can put a stake down there in the bottom, run his stake line, you see his squares here, his plan sheets are here. He can lay that out off that line. So that's why it's important for you, if you're with these guys, you can verify as they're doing it. You don't have to find a partner and go through all this. When we drive pile, we want to drive it continuously as possible, meaning we don't put a bottom in, put 10 bottoms in, come back 2 days later, weld on tops, and try to drive a pile. The piling can lock up, and you won't be able to move it. Well, now you didn't meet your your length requirements, you have no verification of your bearing. So when you start driving a pile, I always tell the contractor, whatever you're gonna put in for bottoms today, you're gonna get tops on and driven in the same day. Don't let bottoms sit overnight because of the potential of lockup. And they do lock up. The worst, well, I should say the best case scenario I've ever seen, we had 130% setup in 2 hours on a pile. That's huge. Very unheard of, but it happens. So that's why we point out and we want you to drive the pile continuously as possible.
If it walks over, you do.
You gotta go back to the engineer and get a permission slip why you can't drive the pile anymore.
Do different soils lock up differently than other soils?
Yes. Clay soils, wet soils, they all act different. Rubbles, rocks, they don't lock up as much. It's because when you're driving a pile, that energy that's going in the pile, it's disturbing the soils around it, loosening them up. And then when you stop driving piling, them soils relax and grab that pile. It's gonna hold it in place. And you gotta excite them soils again to be able to get that pile to move. You know, 30-foot, 20-foot bottom, pretty good chance you could get it started again. But if you had 60-foot bottoms and you have to put another 40 on top, you may not get a 60-foot started again. Yep, it's a lot of pile, a lot of surface area. Remember when we talk about friction, we're looking at surface area, soil's grabbing that pile. So coffer dam. Contractors required to give you extra piling to get piling to cut off elevation. Now this is back to Dresbach again. Can we read this number here? 150, 55, 160 feet, let's say in the leads. Because our cutoff elevation is 54 feet below where we're standing. So we have to be able to get that piling down that far, because that's where they're assuming, on this project, we had to get it to bedrock. I believe we had to get it to bedrock. And bedrock was like 90 feet below cutoff. So and these were open-ended, there was no plate on them. So they were driven open-ended to be able to get to those depths. And then the contractor do piling cleanout, 60 feet down inside of that pile to pour the concrete inside of it. So that's another cost on the contractor is to provide extra piling to be able to get that down there. There was about 30 and 34 pile in these substructures. So use an airlift. You ever seen an airlift? Anybody see how an airlift works? So you got a rigid tube, usually it's aluminum. It could be 20 feet long, 60 feet long. And they plug the air hose into the top of it at the angle. Turn the air hose on and it creates vacuum up here at the angle. So you have your piece of pipe coming down like this, then usually a 90 on here, and then you have an air inlet in here. It comes into your air hose, and it turns the air on, and is pushing air this way, which creates a vacuum that way. So then they can vacuum out the soils. They just hook this to the crane, it's up here rigged up to the crane, and then they can just vacuum out the bottom of the piling. What's that?
They put like a little wing stuff under there and just to go.
Yep, it agitates it, and it's just a giant vacuum cleaner. So in our plan sheet, we identified cobbles and boulders. That's a big thing when you're doing open-ended driving or drilled shafts. So you have to identify sizes of cobbles. And there's cobbles and stuff that we couldn't vacuum. They were bigger than their vacuum. So they literally sent divers down with a 5-gallon bucket, pick rock on the bottom of the pile to get to 60-foot elevation.
No.
Right? So, provided our material, apparatuses capable of withstanding driving to substantial refusal. 5 inches per blow or 240 blows per foot. If you're driving a pile and it stops, and the contractor stops. Yep, we hit substantial refusal, the pile's not moving anymore, we're done. And you as the inspector say, nope, you need to continue driving. If something happens, something breaks, the hammer, the piling, anything happens, you're on the hook as the inspector. This is the max we will ever drive a piling to, is substantial refusal. So remember that, what substantial refusal is. 0.05 inches per blow, 0.5 inches per 10 blows, and 240 blows per foot. And when we start talking about blow counts, we gotta be clear when we're talking per blow or per 10 blows. And it's all simple, just move the decimal, right, per 10, measured in 10. Again, we tell them to continue driving beyond substantial refusal, we're on the hook. Pre-boring through embankments. So you're out in virgin territory, you're building a brand new highway, you built up embankments, you excavated for your foundations. Contractor goes to drive the pile and gets it 3 feet in the ground. We did such a good job compacting our soils, we can't get the pile to go through the embankment. So the contractor is on the hook that he may have to pre-bore to get through that layer down into the virgin ground. So the piling can take off and dry. And when they pre-bore, it has to be just a little bit bigger than the piling, because we don't want to account for the friction or that soil touching that piling until we get down to the virgin soil. Pre-bore. Dry piles on the planned location for test piles. Remember I said we want to drive it as continuous as possible? If you are 125% sure you're not going to have setup, you can delay it. But on the test pile, that's the first pile that goes in. We drive it from start to finish to determine what the rest of the foundation is. So you as the inspector, it's not your job to be in the pile, in the leads, marking the piling, things like that. That's why there's pile bucks. It's their job to be down there next to the pile, marking every 10 blows and giving you a measurement. When the pile hammer is shut off, then you as the inspector can walk in with your tape measure and verify its dimension. But you don't have to be down in that pile hammer during driving. And I highly recommend you stand upwind from a pile hammer. What else about that? Have a conversation with your pile bucks. As we get learning about piling, you're going to know your requirements for bearing on a piling. What your stroke height is and what your dimension is for 10 blows. Have that conversation with the pile buck so he's aware of what we're expecting to meet bearing. So he's just not driving freely, and he'll come back and say we're driving it too hard. And then that's always in a conversation, I won't say argument, but it's a conversation that always gets brought up. You're driving it too hard, you're driving it too hard. Well, according to my documents, I'm not. So definitely have that conversation with the pile buck, what you're looking for dimensions. This is what the pile buck does. Marks it for 10 blows. He'll look at you as the inspector, he'll say 5.5, 4.25, whatever. He'll do some hand signals to tell you what he's got so you know if you're close. And then if he satisfies your requirement, they stop the hammer, you go down, before they take the leads off, you go down with your tape measure and validate his dimension. Because if you say you got it, they take the leads off and you go measure it, he blew his measurement by 1/4 inch, and that was enough to take you out of spec, they have to put the leads and everything back on there. So try to do it before they remove the leads. Load testing. So on big projects, there's a number of bridges. In Minnesota, I got a whole list coming up here. They drive a pile in the ground, they put this big framework on there, they light off an explosion to see how much the pile moves. So when you have on big projects, like Dresbach, we had 180 piling on that project, just on the river piers. if we can do a full-scale mock-up to validate bearing, it's a huge cost savings, because you're not driving the piling as deep, and you're probably not driving the piling as far. So the contractor can elect to do these testing requirements, not, what's that? Oh, okay. So the contractor can, at any time, do any of these load testing. And generally, you have to have a substantial number of piling for it to pay for itself. And it's usually at no cost to the department. Sometimes the department will say, well, this will be a cost savings for us. We're gonna pay for it. You will do it. So this is a stat dynamic test. There's a piling down here. They set up some framework, put some weights on there. You can see our piling right here. Put these counterweights up here across this, in the sleeve here. So it's all set up. The guy's counting down, he's gonna fire it. So now if we watch this weight, right here, it's gonna go up and lock in place. There's the explosion. There's our weights going up. You know, we're talking upwards of 80,000 pounds, 60,000 pounds of weight we're shooting. These are words. So here's a live video. So this is out on the pier. See, there's our piles supporting our platform, and then our test piles right in the middle of this, right here. It's all weight here, and there's going to be an explosion in here. So they're measuring how much that pushed the pile down. We'll watch it again. It's fun to watch. We did 3 of these in Brother. A lot of energy, right?
That's about that.
Not too bad. We're in the river valley, so it's pretty big echoes.
How far did you go down?
This much? That much? Yep. So these are some of the projects we did it on. Dakota had one, Dresbach we had 3, St. Croix did one laterally, and they saved $6.5 million on that pile. Average cost to do it, about $50,000 to $60,000. So if you can spend $50,000 to $60,000 to save that, MnDOT's probably gonna write it in the spec to do it, right? So that's one of the arbitrary things we can do for testing when we have high capacity piles, a lot of piles, deep foundations. So foundation piles. Want to guide piles during driving. Complete pile driving, required batter, plumbness, within a ½ inch per foot, within 6 inches of plan location. And if you get something that looks like this, what do you think we should do? So, first off, what kind of abutment is that? Do we think that is? The weak way or a strong way? Okay, we say it's a weak way. You think that's gonna move?
No.
Agreed. Do you think they're within their 6 inches of planned location?
No.
What should we do?
Cut them off and re-drive them up and trade them.
Cut them off? Let's see,
Cut them off.
there's 85 feet, that's an 85. 85 feet in the ground. Call the engineer,
Yeah.
right there. Call the engineer. But that's not good. You know that you can hit boulders, obstructions, you can hit something subsurface that are putting the piling out of whack.
What typically would the engineer recommend in that situation?
So in something like this, you're gonna increase the size of your footing and your abutment wall.